I have a habit of speaking too soon because before I prove the hockey stick identity, there's a few things I need to clear up about factorial, combinations, and I want to talk about Pascal's triangle, as well as the binomial theorem. Okay, first off, the factorial. 0 factorial is 1. Let me show that. So remember that n factorial is n times n minus 1 all the way down to 2 and 1. So a pretty easy identity that comes out of this, what happens if I divide this whole thing by n? Let me switch colors. If I divide this whole thing by n, then what am I going to get? I'm going to get n factorial over n equals, well, these guys are just going to cancel. The only thing I'm going to be left with is n minus 1 all the way down to 2 and 1. Well, this is just n factorial. So n factorial over n is n minus 1 factorial. Okay. Well, 1 factorial, well, that's just 1 down to itself. So what is 0 factorial? Well, that ought to be 1 factorial over 1. Just by this identity, that will give you 0 factorial. Well, 1 factorial over 1 is just 1 divided by 1, which is still 1. So that is a way you can show that 0 factorial is 1. Another way you can think about it is the factorial describes the number of ways you could arrange a set with n elements. And if you have a set with 0 elements, there's only one way you can arrange it, and that's just by itself. It's kind of trivial, but that's just how you can think about it. Okay. So 0 factorial is 1. Okay, another thing. Combinations. I briefly mentioned this, and I said not to worry about it. But I just want to bring it up again because we actually are going to use it. If you have n choose k, well, that is n factorial over n minus k factorial times k factorial. And this represents how many ways can you choose k objects from a pool of n objects. But there's a catch. What happens if I were to ask you how many ways can you choose 7 objects? Again, and also this is without replacement. I'm sorry. Yeah, without replacement. So once you choose an object, you can't choose it again. So how many ways can you choose 7 objects from a pool of 3 objects? And the simple answer is you can't. There are 0 ways to do it. You can't choose 7 distinct objects from a pool of just 3 if you're doing it without replacement, and the choose function happens without replacement. So if you have like 3 choose 7, that is 0. So you wouldn't even need to substitute into this formula. If you see that this number on top is smaller than the number on the bottom, it's 0 because you can't choose 7 objects from a pool of 3. And that's kind of how you need to think about combinatorics. These things are more than just functions. They actually represent real-world phenomena. So if it doesn't make sense, then you have to think outside the box. So that's out of the way. 3 choose 7, or n choose k is equal to 0 if k is greater than n. Okay. That's out of the way. Okay, now let's talk about Pascal's triangle. You can draw Pascal's triangle by starting with a 1 here and 2 1s here. And then what you do is you add subsequent terms. See how I'm doing this? Hoping you get the gist by me just drawing it. I don't want to talk over this. I just want you to see how I'm drawing this. So this is how Pascal's triangle is drawn. It's actually quite interesting. I'm going to do it without the lines connecting them. And so on. It keeps going. And there's actually lots and lots and lots and lots of patterns that show up from Pascal's triangle. And you can see it's symmetrical about an axis. It's symmetrical about the middle. And these actually represent choosings. They represent binomials. So this is 0, choose 0. This is 1, choose 1. I'm sorry, 1, choose 0. This is 1, choose 1. This is 2, choose 0. 2, choose 1. 2, choose 2. This is 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3, and so on. 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, 4, choose 4. So the Pascal's triangle actually has this choose function kind of built into it. And one pattern that pops out of Pascal's triangle, which I will prove, is it's called the hockey stick identity. If you draw a hockey stick like this, then this guy plus this guy plus this guy equals this guy. So 1 plus 2 plus 3 equals 6. If I continued Pascal's triangle, so 1, 5, 10, 10, 10, 5, 1, I can do it again. I will prove this in the next video. So 1 plus 3 is 4, plus 6 is 10. This is the hockey stick identity. And one more thing about Pascal's triangle is that everywhere else is zeros. This continues. So there's zeros everywhere else. For the exact reason that, see how this is 1, choose 0, and this is 1, choose 2. Well, this is 1, choose 3. Oh, I'm sorry. Whoops. 1, choose 1. This is 1, choose 2. But like I said before, if you have a number that's bigger on the bottom, then that's 0. So you can actually continue Pascal triangles. There's a bunch of zeros above all of these guys. That will become relevant when we prove the hockey stick identity. Okay, last thing I want to clear up, or I want to mention, is the binomial theorem. This is the binomial theorem. X plus y to the n is equal to the sum from j. I usually use j because my naming is the j. I like using j instead of I. So j equals 0 to n of n choose j times x to the n minus j times y to the j. Okay, let's do an example of this. X plus y cubed. This equals the sum from j equals 0 to 3 of 3 choose j times x to the 3 minus j times y to the j. So when j equals 0, this 3 should not be here, it should be here. If I start with the index j equals 0, this is going to be 3 choose 0 times x to the 3 minus 0, which is 3, y to the 0. Now the index when j equals 1, 3 choose 1, times x to the 3 minus 1, which is 2, y to the 1, plus 3 choose 2, times x to the 3 minus 2, which is 1, times y squared, running out of room, plus 3 choose 3, times x to the 0 times y cubed. Okay? Well, how many ways can I choose 0 objects out of a pool of 3? Well, there's only one way I could do it, is just by choosing 1. So the coefficient here is 1. If I have 3 objects and I can choose one of them, how many ways can I do it? 3. 3 choose 2. I'll explain how I knew this off the top of my head at some point, but it is 3. And then 3 choose 3. How many ways can I choose 3 objects out of a pool of 3? There's only one way to do it. It's by choosing all of them. So the coefficient here is 1. And so what you end up with, and y to the 0 is 1, and x to the 0 is 1. So this all simplifies to x cubed plus 3x squared y plus 3xy squared plus y cubed. Let's keep this result in the back of our mind. By the binomial theorem, x plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. Now let's take another look at Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This is the 0th row. This is the first row. This is the second row. And this is the third row. Now, if you'll notice, you start with x cubed, and then you go to x squared, and then you go to x to the first, and then you go with x to the 0. And for y, you start with y to the 0, and then you get y to the first, y squared, and then y cubed. So the way the powers work are pretty simple, but the coefficients, I have 1, 3, 3, 1, which is exactly the coefficients that I have on the third row of Pascal's triangle. And that's no coincidence, because remember, the coefficients are n choose j, or in this case it'd be 3 choose j. And this entry in Pascal's triangle represents 3 choose 0, 3 choose 1, 3 choose 2. This is how I knew that 3 choose 2 is 3, by the way, is because I know that Pascal's triangle is symmetric about the middle, and this represents 3 choose 3. There you go. Also, another way of thinking about it is that n choose k is equal to n choose n minus k. So therefore, 3 choose 1 is equal to 3 choose 3 minus 1, which is 3 choose 2. This is super easy to prove. You can try it yourself. Just plug in these two things to the definition of n choose k, which remember is n factorial over n minus k factorial times k factorial, and you will see that there is symmetry. Anyways, this video is already 13 minutes long. I just wanted to preface, this is the preface for the next video, so this will help you with me proving the hockey stick identity. See you in the next video.